Okay. So, energy stored in an inductor. Oh, alright. So if you imagine this solenoid and it has a magnetic field through it and it has a current in it. Suddenly this current stops. No more EMF is being applied to the inductor, so we have some EMF difference. At, like t equals 5, maybe we have 5 volts. At t equals 6, now we have 0 volts. No more EMF is applied. No more energy is sort of being added to the circuit. But according to our time constant equation, we had some I value, and here's t equals 6. Now suddenly the EMF has dropped and the current tries to go back to 0, back to normal. But the inductor prevents it dropping down instantly to 0. Right, so we still have some current that's like left over. The magnetic field opposes this current just being shut off. So a little bit current is left in the circuit when EMF is shut off. And you might be like, sure, that makes sense. The inductor resists the changing current, but where is that energy coming from, right? Like the EMF is gone. So we still have current flowing, we still have power flowing, but the energy just appears from somewhere. And it's like a weird concept, but the energy is being stored in this magnetic field. This magnetic field has energy in it. A magnetic field doesn't contain energy inherently, but in an inductor it does, because it's keeping resistance to changing back to no current.
So isn't that the same as a capacitor? It's storing it in the magnetic field.
Yeah. I mean,
it's not like the same mechanism.
It's not the same mechanism, but a capacitor stores energy by potentially holding the charges apart from each other. It's just a weirder concept. Like, how does a magnetic field store energy? But anyway, it does. So P equals IV.
Wait, how long does it store the energy?
Until it goes back to 0.
Oh, I see.
Current. So P equals IV, power equals IV, or energy is equal to integral of power dt. So therefore energy is equal to integral of IV dt is equal to integral of I, V is equal to ILdI dt. So this is the energy of a capacitor, inductor, by using integral of power. Yeah, this integral here simplifies, we cancel our dt's and we get integral of ILdI. And I guess this is from current equals current max to current equals 0. It doesn't matter because it's energy, which direction it is, but what's this integral equal to, Jacob?
1/2 I squared L.
Yeah, 1/2 L squared. And whatever, negative or positive, doesn't really matter. So this is energy of a solenoid stored magnetic field. Okay. Or you can also use U, I guess, potential energy.
That's crazy.
What? What's crazy?
No, I was just, it's like that's cool.
Yeah, it is cool. And recall that energy of a capacitor equal 1/2 CV squared. These formulas look pretty similar.
So U is potential energy, right?
U is potential energy, yeah. It doesn't matter which one. And why are we messing with capacitors? That's actually because we are going to put a inductor and a capacitor in the same circuit.
No.
Oh, Lord have mercy.
Oh, jeez.
Okay, so let's use light blue.
No, this is light work. Come on.
Light work. You think? Okay.
No, because this is
Capacitor, inductor.
Just tell me the DI.
Now, what the hell is going to happen here? Well, we'll see. So we're going to try to derive. We're going to look for current of T and voltage of T. What form of equation do you think it is? Do you guys think it's going to be a time constant equation?
Is it gonna be a time constant?
It's not going to be a time constant equation. Do you guys have any other guesses for what equation it might be?
Exponential.
No.
Look what is it?
Is it linear?
It's not linear.
Oh, man.
It's something like once you hear it, you might expect it, but you might not. Do you guys want to
Is it a
spoil the surprise,
polynomial?
or should-
Spoilers.
I think I'm not gonna spoil it because I
Aw.
think it's kind of a fun realization moment. But okay.
I'm not gonna realize shit, bro.
this can be a crazy realization when you do it for me.
Okay.
Wait, let me try first.
No. Okay. So we're gonna start the derivation with energy. Okay. We're gonna have I0. I need to look at my notes here. This is a hard derivation. We have some initial I. Of course, we have EMF here. We have inductance here. We have capacitance here. We're gonna assume resistance is 0. So we have I0 is gonna be something rather, and then we're gonna have voltage 0 is gonna be something rather. But the way we start our equation is with conservation of energy. So we're gonna have potential energy total in this equation is equal to the sum of these energies, 1/2 Li squared plus 1/2 CV squared. And we're gonna assume that energy is conserved because our power, remember power is equal to IV is P equal to IV? I don't know.
That's what you said earlier.
Sure. So V equals IR,
Yeah.
and that means that power is equal to I squared R. How much resistance is in this
Yeah, because
circuit?
power has to equal.
How much resistance is in this circuit?
0.
0 resistance. So there's
Oh,
no
what?
power. Nothing is happening. P is equal to du dt. So the derivative of potential energy is equal to 0. So that proves that the energy is staying conserved because there's no power.
Oh.
So all the energy is staying in the circuit.
That's
All the
crazy.
energy is staying in the circuit. Have you guys guessed yet what equations it will fulfill?
And
Don't-
if there
don't-
were-
don't say-
no,
don't
no.
say.
If there was resistance, because it'd be losing energy, that's why it wouldn't be
Right.
0. Okay, that makes sense. That's
Okay.
a revelation for me. That's,
Alright. So yeah. We're gonna have we're gonna have an initial amount of energy, and that's gonna be equal to UC plus UL. L is the inductor, C is the capacitor, which is 1/2 again CV squared plus 1/2 Li squared. Okay. So let's assume that all the energy first resides in the capacitor. Hold on.
Wait, is the final a quadratic?
No.
Oh. I had high hopes.
So let's substitute some values in. Let's try to make this all fit with charge. So how do we change this into charge? Does either of you guys know?
Well, L equals.
I don't think L is going to be very helpful because L is a constant. It's a generic.
Oh yeah, no, but then I is dq over.
I equals dq.
Yes, bro. Yes, bro.
1/2 dq dt squared plus, what about CV squared? How do we turn that into?
V is some over dt.
So what's the formula for capacitance charge thing?
It's
We have Q equals CV.
yeah.
Okay.
Oh, okay. So so it's 1/2 Q squared over C. Thoughts?
Yeah. Correct. All right. 1/2 dq dt squared plus 1/2 q squared over c is going to stay constant. Okay. Oh, sorry. Forgot my L. Yeah, right here. And that's all going to be equal to, since we said that the energy all stays in the capacitor beginning, qi squared over 2c. E dt of all this.
Oh, okay, yeah.
Any help here?
I mean, qi squared over 2c. I mean, that's just gonna be 0.
Right.
Yeah. And then like the other part.
Oh.
Well, I mean, that's gonna be. It's gonna be.
Let's start with the right.
So you gotta do the product rule right there. That's 0.
Jacob, what's the
That's
derivative
0.
of this?
That's 0.
No, we're taking derivative of q
What?
with respect to time. Qi is 0 because it's initial q. That's a constant. Q squared will have a derivative.
Q over 2c.
You forgot chain rule. 2q dq dt.
Oh,
Right, because we're doing it with respect
yeah,
to c.
yeah.
Over 2c. Okay, cancel the 2's. Nice. Plus, what's the derivative of this one? Something similar.
Product?
Oh yeah, and it'll be 2 dq dt g squared q, or I mean dq squared over d
Oh,
squared.
yeah.
So this could be a second derivative.
So yeah, it'd be d squared q over
Times.
Dude, I hate that so much.
I know. What would be a logical next step?
I mean, now that you put one side on the other.
Oh, God.
Don't you think there's a little bit too many dq dt's in this equation?
No. Looks great to me. I mean, you
can
could
just divide
multiply
them all.
both.
You can
Okay.
just divide them all.
Really? Oh
Yeah.
yeah, no, you're right. And then you could also take.
Yeah, the cancel the 2's.
Cancel the 2's, but also like ever think about the DTs? You could take the DTs out.
I don't think you can do that. No.
It'd be fine though. Yeah, it'd be
It'll be
fun.
funny. Alright. Now we can rearrange. Let's try to get q on one side because that's the thing we're solving for.
Sorry, I mean for Q on one
Jacob,
side.
come on, you can do this.
Minus in the times.
Minus and times? Times what?
C.
Yes,
Um,
sir.
negative
Oh,
Q.
I got that one.
Equals L C D squared Q.
They ain't
dt squared.
believing us.
Okay, then let's get rid of the negative and move it over.
That would be crazy like that.
Q equals negative L C D squared Q
That
over
sucks.
dt squared.
That sucks.
Okay.
That
Does
sucks.
this differential equation start looking like something you've seen before?
It looks like a time Oh, that's not good. That looks like.
Capacitor and inductor oscillate in simple harmonic motion. Spring.
Oh my god!
So yeah, this fulfills the differential equation,
No. Is it
which
sine?
leads into
It's cosine, bro. Sine, bro. You can't do this.
Q equals a cosine of
Oh.
phase shift plus angle of velocity times t.
Dude, that looks
Yeah.
crazy. That looks similar to.
Phase shift,
This
bro.
is the solution
What is
to
that?
this equation.
That's also the.
It's like an
the-
apex
the-
ability, dude.
Fuck. The spring harmonic motion.
Exactly, that's what it is.
Oh.
The formula to get this is when you have some value n is equal to negative angular frequency squared times d squared n dt squared, you can turn it into this, where I guess you
Is
have,
this
this is n. This is differential equation, sort of. Yeah.
It's like an analog, you know.
Right.
which equation
So,
should I
and so
write
that
down?
double, that omega right there, that would instead be the square root of LC.
Yep. So omega will be
God,
square root
bro.
of C.
But then where does the negative come in?
The negative is just part of the equation here.
Oh, my bad. My fault.
Is
Yeah.
this still ENM?
This is freaky, you know, bro.
And then this here,
We're
This
getting
is just
extra
equal to-
nasty stuff.
Q max. So this is our equation for the charge of a capacitor. And you get rid of phase shift, that doesn't really matter. Yeah. QC of a capacitor is equal to Q max times cosine T squared of LC. And you can say the same thing about pretty much everything else in the circuit. But we're gonna have to take some derivatives. So I'm using way too many colors here. This is not good. I is equal to dq dt. So what's the derivative of this?
It's the derivative
Take the derivative of this perspective.
of course. It's
Right.
it's square root LC times Q max cosine T and whatever.
Sign, negative sign.
Oh, negative sign.
Good job, Jacob.
No, good job to me.
Yeah, he got the negative sign. You didn't. I'm just kidding.
You're
Alright.
failure.
So
So yeah, and then we have voltage. Voltage is just similar to this, but it has some coefficient, right? So Q is equal to CV. So to get voltage, you just multiply both sides by C. Voltage is equal to C. Oh, sorry. And we divide both sides by C. There you go. Voltage is equal to Q over C is equal to all this Q max over C cosine T squared LC. Or you can change this just to V max, luckily. Okay. Equation for voltage, equation for current, equation for charge. This is all in the capacitor. And then, you know, we do the same thing for the inductor. The inductor just will be equal to the total potential energy minus these, right? So, I mean, not charge, but the current in the inductor will have to add up. Well, so I guess the current in the inductor will be negative of the current in the capacitor. Or the same, depending on how you look at it. And then the voltage is just equal to Vmax minus the capacitor's voltage, right? This Vc plus Vl has to be equal to Vmax. Big thing is that LC circuit is simple harmonic motion. And we have angular frequency is equal to square root of LC. That's the takeaway.
Oh, hell yeah.
You know, I realized it's funny. I could like write anything on the whiteboard, and you guys would believe me. I've gone on complete tangents before. Just yapped about something that made absolutely no sense because I was confused about the thing I was teaching. You guys like, yeah, sure, that makes sense. I could like just start talking about like anything.
You should see how far you could push
Yeah,
it.
that'd be
before
funny.
we notice.
Said that my neighbor fool say.
That would be funny.
That would have been great. Yeah.
Maybe
So then we
if
take the 14th integral.
Oh, okay.
Yeah,
Makes
sure.
sense.
Yeah, you can do n integrals. Yeah.
Yeah, you wanna
Okay. All right. Sick.
Oh, thanks, Matt.